Hi, everyone. Okay, it's been a while since I've made a video, so don't make fun of me because I'm going to do this in one take and one take only. So we're going to start by looking at the molecular bonding and molecular structure that you guys picked up on your way in today. It looks like this. And then I also want you to have out your VSEPR theory molecules worksheet and the molecular geometry chart if you'd like. And then let's take out our periodic tables as well. I don't have my AP chemistry periodic table, so I'm going to use this one. All right. I also need a pencil. I left everything in the calm room. Okay. All right. So I want to go through a couple examples with you guys because we went to the calm room today for the last half of class. I felt like some of you kind of walked out of here going, oh, I'm not prepared for my quiz tomorrow. So hopefully this video will be helpful to you. So let's go ahead and start with this one here. And my fifth period, we went over N2, but my fourth period, we didn't. So I'm going to start with that example. So if you're in my fifth period and you want to fast forward a few minutes, go ahead. But here we go. So on your quiz tomorrow, I'm going to pick 3 of these. And I'm going to ask you to calculate valence electron number for the entire molecule using your periodic table. Then you will draw out the Lewis structure, make sure every atom has a stable octet. And if you have to move around lone pairs to create some multiple bonds, you can. And then lastly, you'll determine the shape of the molecule, remembering that lone pairs are invisible. So we're looking at the molecular geometry there. We're not going to test on electron geometry, so just focus on molecular. Do that. Okay, so let's start with the N2 example. Hold on, it's behind me. Okay. Sharing this cost. Like I said, I haven't done this in a while. Okay. And I really hope this works because Miss Appleby has like 7 minutes to do this video, and then I got to go get Emily from school. So, okay, we've got using VSEPR theory, name and sketch the shape of the following molecules. Starting with N2, I have 2 nitrogens that are bonded to each other, and nitrogen is in group 5A. So each of those nitrogens are going to have 5 valence electrons. So 5 times 2 is going to give me 10 valence electrons total. Now, the interesting thing about N2 is there's no central molecule. So we're going to do the best that we can with the 2 elements that we have to connect together. They're going to be connected by at least a single bond. That takes 2 of my electrons. I've got 8 to go. And now we're going to start satisfying octets from the outside in. So I'll start from the left. This nitrogen has 2 electrons, 2 more, 2 more, and now that is 8. 2, 4, 6, 8. This nitrogen is happy. I used 6 more to do that. And oh no, I only have 2 electrons left. That's my 10. 2, 4, 6, 8, 10. But this nitrogen only has 4. So I'm going to have to use a multiple bond here. So I'm going to take this set of electrons here and bring them over to this side, drawing in a double bond. Okay. And still, this nitrogen only has 2, 4, 6. Sorry about that. The bell just rang. Yay, you're released from 6th period. Okay, so now in order for both of these nitrogens to have access to 8, I'm going to use a triple bond. So I'm going to move this pair of electrons right here. Okay, and now I've used 2, 4, 6, 8, 10. Did someone just come in the door? I'm going to ignore them. I'm sorry if that's you. 2, 4, 6, 8, 10. I used all 10. And now this nitrogen has 2, 4, 6, 8. This nitrogen has 2, 4, 6, 8. But remember how we talked about how lone pairs create that big electron cloud, right? So we're really seeing this huge electron cloud kind of making a force of electronegativity around. And those 2 forces being negatively charged are not going to want to be next to each other like this if they can help it. In fact, they're going to want to be as spread out as possible. So instead of those two being up there, I'm going to bring them down to the outsides of the nitrogens. So I'm just going to move them here. Okay, still putting out like a big force of energy, but now we have a molecule that is symmetrical. We have one that has all the valence electrons. And if I were to determine the shape of this molecule, I would say that it is linear. It's a line, it's just a linear molecule. Okay, let's do HF. HF is going to be, again, just an H bonded to an F. This is actually hydrofluoric acid. Oh, something's in my eye. Oh my God. Sorry, I had deep blue on my eyes. I can't believe that just happened on camera. Okay. Oh my gosh, I have 4 minutes. Okay, everything's fine. So with HF, we have an H that has 1 valence electron. It is burning. And then an F that has 7 valence electrons. So 1 plus 7, you're welcome, is 8. And so my 8 valence electrons, I'm gonna naturally use 2 to bond hydrogen to fluorine. Oh my God, like I cannot believe that just happened. Do you remember when I was like passing out lotion and I was like, don't get this in your eye. I'm not going to be responsible for any bodily injuries. It's like a jalapeno in my eye. Okay, so I've used 2. I have 6 left. Hydrogen is satisfied with 2. Fluorine needs 6 more in order to have its 8. And now, boom, 2, 4, 6, 8. I have a octet on fluorine and hydrogen is here. Now, what's happening? Remember, these lone pairs, they're all super attracted to fluorine because it's extremely electronegative. However, they're not going to be going over to hydrogen. So we'll see a polar molecule here because they're not the same on both sides. If I were to draw those arrows of polarity, I would draw it going this way, just like we did on Tuesday. Hydrogen at a 2.1 and fluorine at 4. So this is a linear molecule. The shape is linear. However, polarity-wise, it's going to be polar because there's going to be electron density on one side compared to the other. 2 minutes. Okay, last one we're going to do. You're not going to have anything like this on your quiz tomorrow, even though I think you could technically do it. This would be a carbon with 3 hydrogens attached to it. And then you attach an oxygen to the carbon, and then you attach a hydrogen after that. But we're not going to do that. Instead, let's do SO3. I think this one's really interesting. Oh my gosh, this is going to take more than 2 minutes, so it's okay. Okay, so SO3. Naturally, I'm going to think, okay, there's 3 bonded oxygens. Is there going to be a lone pair on the central atom? I'm not so sure. So sulfur has 6 valence electrons plus 6 from each oxygen, and there's 3. So that would be 6, 12, 18. So we have a total of 24 valence electrons to go around, which is quite a bit actually. So let's see how that's going to play out. I'm going to have my sulfur in the middle and 3 oxygens attached to it. And keeping that thought of symmetry, you want to make it as symmetrical as possible as you're drawing. And then if we have to use our molecular geometry chart to determine what they're going to look like after, then by all means, we can do that. But for right now, we'll just keep them kind of at 120-degree angles, if you will. Okay, I've used 6 so far, so I've got 18 to go. And now I'm just going to start satisfying octets. So, okay, 6, 12, 18. I have used all of my electrons and oh snap, sulfur is not happy. Sulfur is not happy, you guys. Sulfur is missing a lone pair. It only has 6 valence electrons and it needs 8 in order to be stable. Now, there are 2 elements right next to sulfur that just so happen to break this rule. It's aluminum and boron. They are happy with 6 valence electrons. But the vast majority of the periodic table, they're going to be satisfied with 8. So unfortunately, we cannot leave our structure like this. So here's what we're going to do. We need to as symmetrically as possible, create a double bond somewhere so that sulfur can have access to 8 electrons. And so I'm going to start just by making this one a double bond here. And I can't just add 2 electrons. I have to take them away from somewhere, right? So I then need to take away those electrons there. And now just making sure I still have my 24, which I do. But you might be thinking, Miss Appleby, how did you know which one to pick? And so in this particular case, we're going to say that sulfur trioxide is a molecule that exhibits something called resonance. Resonance means that no matter which way you orient the electrons, they all end up creating the same molecule. So here I have sulfur has 2, 4, 6, 8 electrons attached to it. It's happy. Each of these oxygens has 8. They are happy. However, who's to say if it's the bottom oxygen that gets the double bond, the left oxygen that gets the double bond, or the right? We don't know. And so sometimes you'll see answers that are drawn like this. You'll see one this way, and then same thing, but the double bond is moved to the upper right-hand side, and then there'll be one more. It's going to be the one now. Okay, spread these out a little. I don't want to go too fast. Okay, so we would call these resonance, and when we have resonance structures, we put them in brackets. These brackets are going to overlap, and I'm sorry. Like I said, I'm doing this video in one swoop, so sorry. So you'll see answers that show like this because they're trying to tell you, hey, this molecule actually it exists in 3 different forms throughout nature. It just depends on what position that double bond is going to be in. So let's go figure out using our chart what we say the shape of this molecule is, regardless of the double bond placement. Because remember, the double bond doesn't necessarily change the amount of bonded or of the steric number on the central atom. It doesn't change the amount of electron groups around the central atom. We would still say that this atom or this molecule has 3 as its total domains or as its steric number. So looking at this chart, if I go the steric number chart and I go down to 3, because that sulfur is being pulled in 3 directions, and it doesn't matter which structure you use, it's still always 3 directions. Then we're going to determine how many bonded atoms there are. Well, there are 3. Each of those bonded atoms is an oxygen, even though one of them is going to have a double bond. And there are no lone pairs on the sulfur. So the molecular shape is going to be trigonal planar. Okay, trigonal planar. So let's write that somewhere. Okay, so in closing, if you have a molecule that's bonded to itself, which I believe there's 3 examples alone just on this chart, 1, 2, and 3, you are not going to be using this chart to determine the shape. It's just going to be linear. What you will say is whether it's polar or non-polar. So that was the example between these 2 up here. And if you do have a central molecule, which the majority of these do, the H2O, the CO2, the NH3, CH4, those all have central molecules, then you're going to decide how many groups are there, what's the steric number around that central molecule, and of that steric number, how many are bonds and how many are lone pairs. The lone pairs are invisible, so they don't, they aren't in the overall shape of the molecule. However, they do play a role in what that shape is going to be. So for your quiz tomorrow, you'll be able to use both of these charts. And I have no other time. So that's going to be the end of this video, you guys. I hope you found this helpful, and I will see you tomorrow for your quiz.